Hello. In this lecture, we will see Armstrong's inference rules. So this is the outline of this lecture. First, we will have an introduction. Then we will have a recap of functional dependencies. Then we will see Armstrong's inference rules. We will see a definition for closure. I have referred Principles of Database Systems by Elmaster and Nawade, 7th edition, chapter 15. We have seen relational database design can be done either by analysis or by synthesis. In analysis approach, or it is also known as bottom-up approach, we start with ER diagrams, and from ER diagrams we map it to relations or tables, and then we apply or we test with some conditions. And if the tables satisfy those conditions, we say those tables or relations are in particular normal form. In relation design by synthesis, we start with a universal relation with a set of attributes that can be a part of a particular database. For example, if you want to design a college database, we start with all the attributes that can occur in that database. So student name will be there, admission number will be there, phone number will be there, parents phone number, faculty name, pen number of faculty, departments. Like that, there will be hundreds of attributes. So we'll start with the set of attributes. Then what we do is we try to find out the relationship between these attributes, or we try to find out the functional dependencies among these attributes by understanding the meaning of these attributes. So we know a student name will definitely depend on admission number. A student phone number will depend on admission number. Like that, we try to find out the different functional dependencies among these attributes. So we'll have a set of functional dependencies there. Then what we do is we try to infer or we try to derive new functional dependencies from this set. And afterwards, we apply algorithms to normalize into third normal form or BCNF. So this is the way we do in relational design by synthesis or top-down approach. So I have mentioned that we start with functional dependencies. So this is an important part in relational design by synthesis. So we should thoroughly understand these functional dependencies. So if you want, you can refer the previous lectures. So I have already defined this functional dependency. It is a set of attribute X will functionally determine a set of attributes Y if the value of X determines a unique value for Y. It is denoted using X arrow Y. This means Y is functionally dependent on X or X functionally determines Y. This holds if whenever tuples have the same value for X, they must have the same value for Y. So we have already seen if there are two tuples T1 and T2, and if the X value of both those tuples are same, then Y value will also be the same if X to Y holds. That is, Y is functionally dependent on X or X functionally determines Y. So this is a constraint to all the relations of that particular relation. So X to Y is a constraint to that relation. So this should hold in every instance of R. That is, if we try to modify or if we try to insert or if we try to delete some tuples, this condition should hold. Then we say X, Y is functionally dependent on X or X functionally determines Y. So next is what is inference for functional dependencies. So a functional dependency X to Y can be inferred or implied by another set of dependencies F specified on R. That is, here we start with a set of functional dependencies F and we try to infer new functional dependencies from this set F. X to Y is such a functional dependency. So this X to Y should hold on every instance of this relation. So if X to Y holds in every legal state of R, then we can say X to Y is inferred from F. That is, whenever R satisfies all the dependencies in F, X to Y will also hold in R. So given a set F, we can infer additional functional dependencies that will hold in whenever the functional dependencies in F hold. So we have a set F. We can apply some rules and we can infer or derive additional functional dependencies. And these functional dependencies will also hold in that relation. For example, so we know that the manager SSN is dependent on department number, or department number functionally determines manager SSN value. And we know that manager phone is dependent on manager SSN. So from these two functional dependencies, so this is our F. From these two functional dependencies, we can infer a new functional dependency, department number to manager phone. So this we have already seen. This is known as transitive dependency. So from these two functional dependencies, we have inferred a new functional dependency. So this is the inferred functional dependency from this, or this is implied by this set. Also, we have seen this example also. We have two functional dependencies in this set. In this relation, we have a functional dependency SSN to ename, comma, birth date, comma, address, comma, department number. We have another functional dependency, department number to dname and dmanager SSN. So from these two from this F, so F consists of two functional dependencies. So from this F, we can infer new functional dependencies like SSN to dname. We have already seen this is transitive dependency. We can also infer SSN to dmanager SSN. Like that, we can infer D number to D name. D number to D name is a functional dependency. Then D number to D manager SSN is a functional dependency. SSN to E name is another functional dependency. Like that, we can infer many other functional dependencies. So closure. So closure of a set F of functional dependency, it is denoted using F plus. It is a set of all functional dependencies that can be inferred from F. So we have seen, we have inferred only 3 functional dependencies. Like that, there may be 15 or 20 functional dependencies that can be inferred from this set. So F closure means all the functional dependencies that can be inferred from this F. So we apply some rules and it helps infer all the functional dependencies. Then we call that set F as F plus or closure of F. So that is the definition for closure. So closure of a set F of functional dependencies is the set. It is also another set F plus of all the functional dependencies that can be inferred from F. So it is a set of functional dependencies which is inferred from this F. So inference rules. So we use inference rules to infer this functional dependency. So it is actually a systematic way to infer dependencies. So inference rules are actually a systematic approach to infer these dependencies. So before going into this Armstrong's inference rules, we should understand some notations that are used in this inference rules. The first notation, this is a symbol that will be used. So F is a function dependencies. This symbol denotes inferred by or implied by. So from F, we have inferred a new functional dependency x to y. So this is used to denote that the functional dependency x to y is inferred from the set F. So this is a symbol that will be used to denote this inference or implied by. So another notation we use for convenience is if we have a function dependency x comma y to z, this can be abbreviated like this xy to z. So the meaning is x and y are two sets of attributes. X is a set of attributes, y is another set of attributes. So z is function dependent on both these attributes. So this can be denoted by xy comma z. Or if we have a function dependency like this xy x comma y comma z to u comma v, it can be abbreviated to xy z to uv. So this denotes x is a set of attribute, y is another set, z is a set of attribute, u is another set, v is another set. So these are some of the notations that we use. So Armstrong's axioms. So actually, these are not axioms. These are actually inference rules. So Armstrong wrote these axioms in 1974. So these are actually inference rules. So if you remember this, axioms in mathematical sense means known facts or given facts. So actually, here the given facts is a set of functional dependency f, and from that f, we apply this Armstrong's inference rules and try to infer new functional dependencies. So these Armstrongs are not axioms; they are actually inference rules. So these are rules to infer new functional dependencies from that f. So we will see one by one. So first inference rule is we call it as reflexive rule. IR1, inference rule 1. It is also known as reflexive rule. So it states that if x is a superset of y, then y is functionally dependent on x. Or we can say if y is a subset of x. So this y is a subset of x, then x to y or x functionally determines y. Or we can say y is functionally dependent on x. So the name itself says it's a reflexive rule. Reflection. It is like looking into a mirror. We can see the reflection. So here y is actually subset of x. So x contains y. So set of attributes, or we can otherwise say that set of attributes always determines itself or any of its subsets. We will see with an example, then you will understand. So another thing to note, a functional dependency x to y is trivial. What do you mean by this trivial functional dependency? So a functional dependency x to y is trivial if x is a superset of y. So if you remember, if you have gone through the text, if you have seen the definition of third normal form, general definition of third normal form, there it is mentioned that every non-trivial functional dependency x to a, either x is a super key or a is a prime attribute. So x to a should be a non-trivial functional dependency. So what do you mean by this trivial functional dependency? So if y is a subset of x or if x is a superset of y, then it is trivial. Otherwise, it is non-trivial. So we will see this reflexive rule with an example. So we have a relation student with admission number, name, date of birth, and address. So if you have a functional dependency, admission number to name, comma name to name, then we can see that name is a subset of this admission number, comma name. So name is a subset of admission number, name, comma name. So the reflexive rule can also be stated as x to y, x to x. That is, a particular attribute or a particular set of attributes functionally determines itself. A particular attribute determines itself. That is, admission number is not admission number itself. Or admission number functionally determines admission number. So this is known as reflexive rule. So here, name is a subset of this. So this functional dependency will definitely hold in this relation. So any set of attributes functionally determines itself. Then we call it as reflexive rule. For example, name to name, there is a functional dependency. Admission number to admission number, there will be a functional dependency. So that is IR1. Then next is IR2, inference rule 2. It is also known as augmentation rule. That is adding something. So it states that if there is a functional dependency x to y, this implies x is set to y is set. That is, we can add the same set of attributes in LHS and RHS. Then also that functional dependency will hold. That is, we have a functional dependency x to y. If we had a same set of attributes in LHS and RHS, then also that functional dependency will also hold in that relation. So this is known as augmentation rule. So adding the same set of attributes to both the LHS and RHS of a dependency results in another valid dependency. This functional dependency is also valid. So it can also be stated like this: x to y. Then we can simply add the left side only. X is set to y. So this functional dependency will also hold. This is also augmentation rule. Even if we are not adding anything to the RHS, we are simply adding a set of attributes to LHS. Then also this functional dependency will hold. So this is known as augmentation rule. So augmenting the left hand side attributes of a functional dependency produces another valid functional dependency. So you may ask whether x to y set also holds. So that functional dependency will not be there, may not be there. We are not sure that whether it will happen or not. It will depend on the relationship, or it will depend on the meaning of those attributes. So this will definitely hold. Adding some set of attributes to LHS will hold, but the other way it does not hold at all. So this is an example. We will see the same example. We have admission number to name of functional dependencies there. We can add, as per IR2, we can add the same set of attributes to LHS and RHS. So we have inferred a new functional dependency, admission number comma date of birth, name comma date of birth. So this is augmentation rule. Or we can simply add a attribute or a set of attributes to LHS alone, left hand side alone. Then we can infer a new functional dependency from this one. So this is IR2, inference rule 2, that is augmenting attributes to LHS and RHS, or augmenting to LHS alone. Then third, it is inference rule 3, we call it as transitive rule. So we have already seen this transitive rule when we define third normal form. So IR3 states that if there is a functional dependency x to y and y to z, then we can imply that x to z will also hold in that relation. So if there is a functional dependency x to y and y to z, then definitely x to z also holds. This we have already seen, and we have already seen this example also. In this we have these two functional dependencies: SSN2 e name, birth date, address, d number d name, manager SSN. So we have a function. We can infer that SSN to d name is there. This is inferred using this transitive rule, and also SSN to d manager SSN, because there is a transitive rule. This is x, this is y, and this is z. So x to z will also hold. SSN to d name and SSN to d manager SSN also hold. So this is transitive rule, or IR3. So IR1 to IR3 is considered to be sound and complete. We'll see what is sound and what is complete. So IR1 to IR3 is sound. So given a set of functional dependencies F specified on R, any dependency that is inferred from F by using IR1 to IR3, by applying these three rules, will also hold in every relation state of R. That is, if you have a F specified on a particular relation, and any dependency that is inferred from this F by applying these three rules, all those functional dependency will also hold on that particular R. So that is why it is known as sound. Then IR1 to IR3 is also complete. That is, applying IR1 to IR3 repeatedly on F. If you apply all these three rules repeatedly on F, it results in the complete set of all possible functional dependencies that can be inferred from F. So if you want to infer all the functional dependencies, or if you want to find the closure of F, we have already defined closure. So closure is the set of functional dependencies which can be inferred from F. It is a complete set of functional dependencies. So by applying IR1 to IR3 on that F, by repeatedly applying on that F, we can infer, or we can find the complete set of all those functional dependencies. Or we can find out this F plus closure of F can be determined from F by using only IR1 to IR3. By using these three rules, we can find closure. Then we have three more inference rules. Next is IR4. It is also known as decomposition or projective rule. So it states that if there is a functional dependency x to y is set, this implies that x to y will also hold. It means that if there is a functional dependency x to y is set, then x to y also holds. Or we can say that if x to y is set is there, x to y and x to z holds. For example, if there is a functional dependency x to a1, a2, etc., an, so it is a set of attributes. Then we can infer x to a1, x to a2, x to a3, like that, x to an. So this is decomposition. We can decompose this into x to y and x to z. For example, if there is a functional dependency admission number to name, comma, date of birth, comma, address, we can decompose into admission number to name, admission number to date of birth, and admission number to address. So this is known as decomposition or projective rule. So if there is a functional dependency x to y is set, we can imply or we can infer that x to y and x to z. So this is known as decomposition or projective rule. Then fifth one is inference rule 5. We call it as union rule or additive rule. So this is the opposite of decomposition rule. So if there are two functional dependencies x to y and x to z, here x is same in these two functional dependencies, then we can infer that x to y z also holds. So this is the opposite of the previous one. This is known as union or additive rule. We are adding those two functional dependencies and forming a new functional dependency x to y z. So this is the opposite. We have x to a1, x to a2, x to an. From that, we can infer that x to a1, comma a2, comma up to an. So this is known as union or additive rule. We will see the same example. We have a set of functional dependency: admission number to name, admission number to date of birth, admission number to address. From this, we can infer that admission number to name, comma date of birth, comma address. Or we are doing union operation on the z part, y z part. So we are performing y union z here. Then sixth rule, IR6, it is known as pseudotransitive rule. Pseudotransitive rule. So it states that, so if there is a functional dependency x to y, and if there is another functional dependency wy to z, then this y can be replaced with this x. That is wx to z also holds. So this is known as pseudo-transitive rule. That is, if you have a functional dependency x to y and wy to z, this y can be replaced with this x. So the result will be wx to z. So this functional dependency will also hold on that relation. So allows us to replace a set of attributes y on the LHS of a dependency with another set x that function determines y. So this can be replaced only if x function determines that set of attribute y. So we'll see an example. We have a functional dependency student, admission number, name, date of birth, and address. And this is a functional dependency. We have admission number, date of birth is there. Then another functional dependency is there, name, comma, date of birth to address. Then we can replace this date of birth with x, that is admission number, because admission number function determines this date of birth, and we can replace like this, name, comma, admission number. So we can replace this date of birth with this admission number because admission number function determines date of birth. So this functional dependency will also hold in that relation. So this is known as pseudo-transitive rule. So we have to note a few things. X to A and X to B implies. So if there is a functional dependency X to A and X to B, this implies X to AB by union rule. We have already seen this rule. And also X to A and Y to B. Here X and Y are different. X to A and Y to B implies we can do this union operation XY to AB. So this functional dependency also holds. So So if there is a functional dependency x to a and y to b, then we can do xy to ab. But xy to a does not necessarily imply, certain cases it may imply, but it does not imply that either x to a or y to a. This may not be true. Okay. X y to a, if there is a functional dependency x y to a, it does not mean that there is a functional dependency x to a or y to a. So this is wrong. There won't be any functional dependency like this. So this is a summary. So we have seen 6 different inference rules. First one is reflexive, second is augmentation rule, transitive rule, IR1 to IR3. Those rules are sound and complete because all other functional dependencies can be inferred from these 3 rules. Then IR4, IR5 and IR6. These 3 rules can also be inferred from these 3 rules, first 3 rules. So that is why these 3 rules are known as sound and complete. Okay, thank you.